Welcome back. Good morning for those who haven't met yet today. My name is Roberto Lopez-Anido. I'm professor in civil and environmental engineering here at the University of Maine and member of the Advanced Structures and Composite Center. I serve as the Thrust Area 2 leader in the TIDC project. And today I am honored to be the moderator of the session on novel composite materials in transportation. We're looking to move beyond steel and concrete. I will have some introductory remarks, and then we have 4 guest speakers today that will present different aspects that are key in terms of novel materials in transportation, following by a panel discussion where we're going to have questions from the audience, both who are here and those who are connecting virtually. We're going to start by looking at the issues in transportation and again, follow with the presentations addressing those issues. We have been thinking in terms of how we can come up with a roadmap for implementing novel composite materials in transportation infrastructure. We look at the needs and the potential solutions. What are the needs? We need durable, non-corrosive, lightweight, sustainable materials. What solutions we have out there? We can look at fiber reinforced polymer composites. That will be the focus of today's session. We need advanced manufacturing technologies. What technologies are available today? We're going to discuss large format 3D printing, continuous forming, pultrusion, and other manufacturing technologies. We need to develop cost-effective, move forward. Yep, sorry. Cost-effective solutions for transportation needs. How we do this? We have heard speakers today. We had a great keynote yesterday and another one today, both from the Commissioner of New Hampshire DOT and from the RAID project. We learned that collaborations with industry and DOTs are key for this goal. We need to innovate and we need to validate those designs. And here comes our role in academia. Train students, train personnel, staff, do the modeling work. This is not just trial and error. We need to be able to predict and to design using rational approaches and then verify through lab testing. We need to assess the performance and durability in the field. And for this reason, we need demonstration projects where we implement and we monitor the products that are being used in transportation. And finally, we need to encompass this through a life cycle cost analysis. And here I am using the words from the commissioner yesterday, realize the benefits of the materials and the technologies. And in fact, we're looking, for example, at how to recycle these materials, how to reuse them. Briefly, I will mention 3 projects just to see how needs and solutions can be matched. We mentioned this project before in other presentations, 3D printed diffusers for highway culvert rehabilitation. What is the problem? Well, we heard about the problems. I mean, roads that are closed because of flooding and problems of erosion, the culverts that are being corroded and they need it to be replaced or maintained. The solution was brought forward by a hydrologist from Maine DOT who came up with the concept of culvert diffusers. These are basically gradually flared outlet sections that have the function to increase the culvert capacity and compensate for the loss due to liner retrofits that are used in trenchless repair technologies. But at the same time, we need to reduce the outlet flow velocity to minimize erosion. This was a great solution, but it was lacking the materials and the manufacturing methods. And here comes our role. We marry this with large format 3D printing. It's the ideal application because the diffusers are unique. The geometry, the design depends on the site conditions. No other manufacturing method could be cost effective. Optimized 3D printing solution is what we are implementing here. We are in the 2nd generation of diffusers. We installed prototypes last year in collaboration with Maine DOT. We are doing now a full site installation in collaboration with New Hampshire DOT for a road in Exeter, New Hampshire. The benefit is the reduction in the cost. The project in New Hampshire is a deep culvert, about 20 feet. The excavation would have been very expensive. It would have interrupted the road. Again, this is a project where we can satisfy those needs with new materials and technologies. Another one, and also using large format 3D printing, is making formworks for precast concrete. This was an initiative that came to us from the Pre-Stress Precast Concrete Institute. We had a series of meetings with their partner precasters and fabricators, and we identified one partner here in Maine, American Concrete Industries in BC, not far here from campus, who had a project with Maine DOT, and working together, we designed a set of formwork for a railroad bridge ballast retainer, a precast concrete structure. This formwork was deployed last fall at their facility in BC. It has been used 6 times to cast the modules that you can see here in the picture below. And it's another good example of how we can use 3D printed materials in construction applications for the transportation industry. Something very important is that the material we're using here, about 7,000 pounds of composite material, becomes an asset that can be recycled. And that's exactly what we're investigating right now. How we can chop this material, how we can pelletize it and use it again. So again, this doesn't go to the landfill. This goes back to be reused, but this is not a trivial question. There is energy involved. There are properties that change over time. So what we did is we reached out to the experts in the field, Oak Ridge National Lab, and established a partnership with them to see how we can recycle the materials. We are starting that project, so I hope to have more to share coming maybe in the next transportation conference. Finally, Habib mentioned the thermoplastic composite rebar, and I want to leave this here as kind of food for thought, and kind of motivate discussions. This is a new technology that can address some of the shortfalls of the existing thermoset rebar that basically cannot be bent. And that introduces a number of limitations at the construction site and therefore cost. The thermoplastic rebar with, I would say, modest amounts of heat and pressure can be shaped and bent. We can form stirrups. We can adapt it to the geometry required at the construction site. Now, this technology requires a solution, and the solution implemented here at the University of Maine has been very comprehensive. We brought together a team with diverse expertise. We have mechanical engineers, electrical engineers, and structural engineers came up with a fabrication process that has been streamlined, and Habib showed one of the first prototypes. There are still many steps to move forward to get this product commercialized, but we are getting there. We are marking and checking all the needs and making sure that we can have a product that will have the right surface texture, a product that will have the right properties to be used as concrete reinforcement, and that can be handled and bent in a way that is cost efficient.